Hello everyone. My name is Alireza Borhani and I recently graduated with a master's degree from Amir Kabir University of Technology. In this talk, I will introduce our experience in accelerating neural network training on FPGA. As you know, training a state-of-the-art neural networks requires much memory and computation time. On the other hand, embedded devices usually have limited resources. Therefore, implementing the training on embedded devices is quite a challenging task. Fortunately, FPGA is a promising hardware platform for implementing and optimizing neural networks since it offers high energy efficiency and parallelism. However, implementing neural network training on FPGA has two significant challenges. The first challenge is realizing non-polynomial activation functions, such as the sigmoid activation function. Another challenge is the precision of weights and activations in the ANN model. As I mentioned before, embedded devices have limited resources. On the other hand, although full precision floating point networks avoid any quantization error, they increase implementation costs such as memory consumption, which makes them inappropriate to use in an embedded context. To address these challenges, we propose FAST, a low precision method that utilizes fixed point arithmetic to reduce memory usage and computational cost. FAST first addresses the challenge of implementing the non-polynomial sigmoid activation function by presenting a solution using piecewise nonlinear approximation or PNLA methods. Then it introduces a hardware-optimized PRELU or hope activation function as an alternative to complex non-polynomial functions. Finally, the method provides the necessary logic for performing matrix calculations, saving network parameters, and the results of intermediate matrix calculations. In other words, it allows the complete implementation of feed-forward and backpropagation flows on FPGA. Let's deal with the PNLA method first. Here, the sigmoid function is chosen since it's one of the most widely used and also is challenging to approximate. This function consumes considerable hardware resources since it's a non-polynomial function. Actually, PNLA approximates the desired function by breaking it into smaller pieces and replacing each piece separately with a nonlinear polynomial. To perform PNLA, we approximate the function using second-degree polynomials. To do so, we first break the function into 5 separate pieces. Then we approximate each piece by a quadratic function. To achieve an accurate approximation, the coefficients of each quadratic function should be chosen so that the overall difference between the desired function and the quadratic function becomes minimum. To find the optimal value of these parameters, we utilize the polynomial regression algorithm. However, in order to reduce the required resources, the data format should transform from floating point to fixed point. When transforming the parameters from FP to FXP, the number of bits for fractional part impacts the quantization error. To find the appropriate number of bits for the fractional part, we used the ELMO method and found out that using more than 12 bits for the fractional part has a negligible impact on reducing the error. Thus, we chose this value as the number of bits for the fractional part. However, this transformation still changes the value of the coefficients and results in a quantization error. So, we make an improvement to our method to alleviate the impact of this error. First, the average deviation between the desired function and the quadratic function is calculated, and then the result is added to the quadratic, adjusting it so that the approximation better fits the desired function. Next, it's time to adjust the range of each piece. To this end, for each piece, we check from which point the corresponding quadratic function of the next or previous piece better approximates the current piece than its own quadratic function. Then, we change the highest or lowest value of the range to this point. For instance, in this example, consider piece 2. Before this point, the corresponding function of piece 1 is a better approximation of piece 2, so we change the lowest value of the range to this point. Moreover, after this point, the corresponding function of piece 3 better approximates piece 2, so we change the highest value of the range to this point. This figure illustrates the results of PLNA for the sigmoid function and its derivative before and after the improvement. The error before the improvement is shown in red, and the error after the improvement is shown in blue. As you can see, normalizing the parameters and adjusting the range considerably reduces the approximation error. Now, let's deal with the hardware-optimized p-ReLU or HOPE activation function, which is specifically devised to reduce the required resources and increase the accuracy of computations on FPGA. As you know, p-ReLU is one of the most popular activation functions in neural networks. Since it is only composed of linear pieces, its implementation on FPGA is less challenging compared to complex functions. However, it doesn't introduce the same nonlinearity level as complex functions, and also this function is boundless and unsuitable for the FXB data format. So we modified this function and devised HOPE. These two formulas indicate the HOPE function and its derivative. As you can see, all coefficients in HOPE are powers of 2. Thus, the FPGA implementation of this function can be realized using only combinational logic, namely add and shift operations. Now, here is the last part of our method, hardware architecture. If you are familiar with neural networks, you know that to implement feed-forward and back-propagation flows, we need to compute these formulas in each layer. As you know, during the feed-forward process, the network is fed with a training dataset to generate an output vector. And during the back-propagation process, the error of the ANN is fed backward, which can help find appropriate weights. During this flow, we need to calculate the gradients of the cost function with respect to the bias and weight values. To this end, we need to use this function called delta. Finally, we can adjust the weight and bias values to minimize the loss. To implement feed-forward and back-propagation flows, we need to store these four matrices in the on-chip block RAMs or BRAMs. The weight and bias memory or WBM holds the values of weights and biases. The second memory or ZM or Z memory holds MAC operation output values. The third one holds the layer output values, and the last one, which is called gradient memory, holds gradient values. Let's start with the feed-forward flow first. As I mentioned before, during this flow, we should calculate these two formulas. The first equation calculates the MAC operation using weights, biases, and the output of the previous layer. Then the result, which is stored in the Z parameter, is fed into the activation function phi to generate the output of this layer. This figure shows the data path of these equations for each layer. As you can see, first, each weight is read from the weight and bias memory and multiplied by the corresponding output of the previous layer. Then the result is added to the existing value in the accumulator register. This continues to the last weight, and after that, the bias values are read from memory and directly added to the accumulator register. So now we have the result of the MAC operation in a neuron. Thus, we can store it in the Z memory and also feed it to the activation function phi to generate the output of the neuron. Now, not only the next layer can start its calculations using this output, but only this layer can perform the calculations on the next neuron of it. Therefore, the calculations in layers are performed in a pipeline manner. Whenever the output of the network has been calculated, the backpropagation flow begins. In the first step of this flow, the gradient of the cost function with respect to the bias values is calculated. As you can see in the equation, this value is equal to the multiplication of the delta value and the gradient of the output of the layer with respect to the MAC operation result, which in fact is the derivative of the activation function. So as you can see in the figure, in this step, the derivative of the activation function is multiplied by delta value, which is computed by the next layer. And then the result is stored in the bias gradient or BG buffer. In the second step of this flow, the gradients of the cost function with respect to weight values are calculated. The first part of this formula is equal to the gradients of the cost with respect to bias values, which was computed in the previous step. So we just need to multiply the bias gradient buffer by the gradient of z with respect to the weights, which is equal to the output of the previous layer. As you can see in the figure, the gradients before storing in the gradient memory are multiplied by eta over rho to perform a stochastic gradient descent. Actually, eta is the learning rate and rho is the batch size. Now, in the third step, it's time to compute delta for the previous layer. To this end, the gradient of the cost with respect to the bias values is read from the bias gradient buffer and multiplied by the weights. After performing this MAC operation, the delta value of the previous layer is computed and can be used in calculations of the previous layer. After repeating the previous three steps for all values in the batch, and now it's time to update the weight and bias values using the values stored in the gradient memory. As you can see in the figure, we also add momentum to a stochastic gradient descent by dividing all the values in the gradient memory by 4 by using arithmetic right shift and storing them again. To evaluate fast, we design two separate networks. The first network, which is called sigmoid only or SO network, is a three-layered network with 25, 10, and 10 neurons in the first, second, and third layers respectively. Actually, the third layer outputs a vector with 10 elements representing the confidence level for detecting 0 to 9 digits. All layers in this network utilize the sigmoid activation function. The second network, which is called Hope Sigmoid or HS network, is designed similarly to the SO network, except its first and second layers utilize the Hope activation function. We evaluated fast on Xilinx Zinc FPGA using the MNIST dataset. Both mentioned networks were trained on FPGA using the fast method. Additionally, as a baseline reference, the SO network was also implemented in software and trained on CPU. Additionally, we utilized F-score as the metric to evaluate fast. The result of the F-score metric for each implementation per individual digit is depicted in this figure. As you can see, the SO network is shown in blue, the HS network is shown in green, and the software implementation is shown in orange. The figure shows how well each implementation performs when detecting a specific digit. Also, the pattern of the rise and fall of the F-score per digit is quite similar for both FPGA and software implementations. We also measured the training time per batch of our method. As you can see, FAST offers a training time per batch of 8.9 milliseconds, while the software implementations need 76.8 milliseconds. Thus, FAST can achieve around 8.6x speedup. Finally, we measured the resource utilization of FAST. FAST needs to use 14 block RAMs or BRAMs, which is equal to 63 kilobytes of memory. On the other hand, training the network in software requires around 200 megabytes of memory, and thus using FAST results in a massive reduction in the required memory size. Eventually, the conclusion is that in this paper we propose a low precision scheme which first presents a solution using PLNA to implement the sigmoid activation function. Then it offers the Hope activation function as an alternative to complex functions. And finally, the method provides the architecture for implementing feed-forward and backpropagation flows. The evaluation results indicate that the method requires orders of magnitude less memory and achieves an 8.6x speedup. If you have any questions, feel free to ask now or contact me later.